we will be finishing up the section on lines and linear equations today. That homework, as you can see in my math lab, will be due tomorrow. So if you have not started on that already, please do so. It's due tomorrow by midnight. And we will move on and finish library of functions. That's a pretty quick section. And then we'll talk about graphing with transformations. So let's go ahead and pick up where we left off last time. So last time we talked about example 5 here, which was find an equation for a parallel line. And so we finished that problem, and we're going to go ahead and move on to example 6, which will look different than if you printed out the notes ahead of time. So example 6, I changed the equation that we're looking at, and I changed the point as well. So go ahead and make those modifications if you haven't done so already, if you did print out your notes. So let's go ahead and look at this newly modified example 6 here. So for example 6, let me go ahead and set up this. All right, cool. So for example 6, well, first we need to think about, all right, so we were talking about the conditions for parallel lines. We understand parallel lines visually. Two lines that go on forever, in both directions, and they never intersect, they never cross. So what we ended up doing was we had some algebraic interpretation of this. Since parallel lines are lines, then they have slopes. So that means two lines are parallel if they have the same slope. So that was our algebraic interpretation from last time. We didn't talk about perpendicular. So we haven't talked about perpendicular yet. Visually, I think the same idea is there. I think we all have some fundamental idea of perpendicular lines. It's two lines that intersect and form a 90-degree angle. So we all understand that one fairly well, but how does that translate algebraically? And the algebraic translation is one slope is the negative reciprocal of the other slope. So one slope is the negative reciprocal of the other slope. So if you have one slope, like 2, the slope of a perpendicular line would be, let me just write that one out. So if one slope was 2 for one line, and you wanted to figure out the slope of a perpendicular line, what you would do is you would flip the number. So that's the reciprocal, just flip. So 2, if you flip 2, it would be 1/2. And then you just change the sign. So if it were a negative number, you'd make it positive. If it's positive, you make it negative. So that would be the slope of a perpendicular line. And that makes sense because if a graph was going in this motion here, see on your end that would be positive. If something's perpendicular to it, it's going to be going in a completely different trend relative to this would be negative, a negative trend instead of positive. So the flip in the sign makes sense. And then the reciprocal, that one's a little bit more nitty-gritty to get into, so I won't. But that's the idea. So let's go ahead and look at the next example. Which is example 6, find an equation for the line that is perpendicular to x is equal to -16 and contains that point. So if anything, let's go ahead and try to visualize this initial line that they give us. Now, x is equal to -16. that doesn't really have the form of y is equal to mx plus b. So it doesn't have a y at all. So it's just an x. I feel like we've seen that situation before, when it's just x is equal to a number. In fact, we have. That refers to a vertical line. Remember, vertical lines do not have a slope. This line here that they give us does not have a slope. This is a vertical line. And one reason for determining that is because this line is not in y is equal to mx plus b form. There's no y. That's a dead giveaway. So is this just a vertical line anywhere? No, it's not. It's a vertical line at x is equal to negative 16. So x is equal to negative 16 is going to the left. So it'd be a vertical line there. And so this is the original line. This isn't the perpendicular. We haven't even touched the idea of a perpendicular line yet. So now that we have an idea of what the original line looks like, now we need to figure out what a perpendicular line would look like. So naturally, we have a vertical line. What kind of line would be perpendicular to it? Yeah, you can imagine horizontal. So now we have in our minds, we want to consider a horizontal line. And not just any horizontal line, because we can draw a whole bunch of horizontal lines. We want a horizontal line that goes through the point -7, -1. Let's say that point would go right here. You know, you go to the left 7 and down 1. Let's say it goes right there. And we need a horizontal line to go directly through that. So we want to find an equation for this horizontal line. So the general equation is mx plus b. So we have a horizontal line. We need to figure out its slope. So the slope of a horizontal line, that is 0. So we talked about that Monday. Slope of a horizontal line is 0. So if anything, we have 0x, which I'll fix that in a bit. And now we need the y-intercept. So the y-intercept goes through right there. And from here, we just need to figure out that y value, which it just so happens we were given already. It's -1. And by cleaning everything up, we get that y is equal to -1. So that would be the line that is perpendicular to x is equal to -16, such that it goes through that very specific point. Does anyone have any questions about this so far? Not? Let's go ahead and look at example 7. So this is, as you see, this one's kind of a word problem. So, and if you printed out your notes, the numbers are the same, but they might be swapped. On your notes, it might say 0 Celsius, 32 Fahrenheit, 100 Celsius, 212 Fahrenheit. I switched them. That's the only changes I made. So Fahrenheit is a temperature value that we use here in the States. A lot of other places use Celsius. And what this problem says is that, well, if you wanted to convert from one to the other, then there's actually a linear association between the two. And given that information, they give us what amounts to an input and an output. So since there is a linear relationship between Fahrenheit and Celsius, then we could treat one of them as an X, one of them as a Y. So in particular, we can treat F as X and C as Y, which means now we have an input and an output. 32 degrees corresponds to 0 degrees, or an input of 32 results in an output of 0, and an input of 212 corresponds to an output of 100. So we're treating Fahrenheit like an X value or an input, and we're treating Celsius like an output or Y value. And so what this does is it gives us 2 points on a line. Using that information, we can determine the equation of the line. So if we have 2 points, how do we figure out the equation of a line? So we have 2 formulas. There's point slope form and slope intercept form. Well, both of those, we do not have enough criteria for either of those. Why is that? Because we don't have a slope. I don't see a slope here anywhere. So we have to figure out the slope. So how do we figure out the slope given 2 points? Well, it just so happens it was the very first formula we talked about. Y2 minus Y1 divided by X2 minus X1. Y2 here, we can say that that's 100 minus Y1, which is 0, divided by 212 minus 32. And by simplifying that, you should get 5 over 9 after you simplify everything. I think you get 100 divided by 180, which is 10 over 18, which is 5 over 9. And they will want a fraction instead of a decimal. So with that being said, we have the slope. And so let's go back to those 2 forms. One of the forms is point slope. The other form is slope intercept form. One of these we have the full criteria for, the other one we do not. We have enough information for the point slope form because we have a point. In fact, we have 2 points, but we do have a point. We have a slope. The other formula, we do not have the intercept. So that one doesn't really help us out. We don't know the y-intercept. So we're going to use the point slope, the point slope formula. And if you recall, it's y minus y1. So what is y1? We said that that's 0. It's equal to m, which we found to be 5 over 9, x minus x1, which is 32. Now we can clean this up slightly And also revert back to, well, what was y representing this whole time? Celsius. What does x represent this whole time? Fahrenheit. So we can simplify this as C is equal to 5/9, parentheses, F minus 32. And this problem is a multiple choice problem. So you will notice that as one of the answers if you get a problem like this. So they don't distribute the 5/9. So that's why we're going to stop here for this problem. The problem also goes on to say, plug in 60 degrees for Fahrenheit and determine Celsius. I'm not going to do that, but you just plug in 60 for F. So that one's a little bit easier. You just plug in 60 for F and figure out what your output is. So I'll stop right there for this problem, example 7. Does anyone have any questions about anything before I move on? Google Meets. Okay. All right, so let me go ahead and erase this. Was told we were going to get a new monitor in here. And I've yet to get a new monitor, so I'm hoping by next week there will be a much better monitor in here that actually, when I write stuff, it will actually follow along with the PDF as I scroll. Until then, now we're going to generalize the idea of a line, which really doesn't change much. In fact, this part should be fairly straightforward. We generalize a line to a linear function. And so this is kind of this idea of taking intuitive ideas such as a graph and then relating them to a function. And so you might notice that this formula for a linear function is the exact same as the formula we had before, except instead of y, they just use the fancy f of x notation. But still, nothing really changes. M is the slope and B is the y-intercept. A few notes that I have underneath that. The homework does mention something regarding the average rate of change, but it just so happens for a linear function that it's just the slope. So if you see something asking for the average rate of change, it's just asking for the slope. So don't let that one trip you up too much. Additionally, a linear function is increasing if the slope is positive. It's decreasing if the slope is negative, which is fairly intuitive based off of our understanding of lines. So positive slope, that would increase. Is it the right direction? Yeah, that would increase. Negative slope would decrease, would go down. So that'll answer a few homework questions right there. Let's move on to example 8. So example 8 wants us to just write a linear model, which is just a fancy way of saying write a linear function given all of this information. So we know those generally look like y is equal to mx plus b, or I guess f of x, technically. I'll leave it like this for now. So it means we need a slope and we need a y-intercept. All right, so what is the problem even asking? This company charges $210 to rent a car plus 0.15 cents, or 15 cents rather, per mile driven. Let's see, so all we have to do is figure out which number goes where. Which one of those is the slope and which one of those is the y-intercept? Now, it looks to me the per mile is a dead giveaway that the 0.15 is the slope. And it seems like since 210 is going to be charged no matter what, and that is the y-intercept. The problem also wants us to put it in this fancy notation. It says use C for cost, because this is an application problem. And we're going to do that of X stuff. It's a multiple choice problem, I'm pretty sure, so you will notice fairly quickly which one is which. But that's all you have to do for this problem. Just set up a linear model. And as far as linearity goes, I guess that's a good segue into example 9, where now they give you a table of values, and they want you to determine whether that table of values gives you a linear trend or not, if that's that function is linear or nonlinear. So if you were to plot all of these on a XY plane, this would just be 5 points. 0, -3, 1, -8, all of that. If you were to draw a line connecting all of those, would that give you a linear trend or not? And the easiest way to determine that is determining the difference between the y values. Or in other words, finding the rates of change. So the difference between -3 and -8, so what's that difference? It seems like it's subtracting 5. -3 minus -3 minus 5 is -8. All right, so what's the difference between -8 and -13? Well, that's -5. And then -13 and -18, -5. -18 and -23, that's -5. It's a very interesting pattern. The rate of change, or the change in the y values, is constant. That is a linear trend. Because they are all -5, that means that the average rate of change for them is the same. But we've already said that the average rate of change is the slope. So this is linear. With the slope being -5. It's the constant average rate of change, which we said is the slope. So that'll help you answer a few homework questions right there. Does anyone have any questions up to this point before I move on? Not. I'll continue to this graph down here. So we are given this graph. We are asked to figure out some components about it. So given this graph, we need to figure out A, B, C, and D here. So go ahead and start off with part A. Part A wants to know when the function itself is equal to 0. Well, there's no way to do this algebraically because there's no function. There's no like 5x plus 3 or anything. There's nothing like that. It's we have this function is equal to 0, which in other words means y is 0. Now, when we look at this graph, where is y equal to 0? Seems like it's equal to 0 right there. And when we solve a function, we're trying to figure out the x value. So the x value for this point seems to be -8. And that's how this one starts off. That completes part A. Part B may be a little bit more engaged. So part B wants us to determine when the function is greater than 8. Okay, so that's an interesting way of asking us that. So I guess a good starting point is, where is the function equal to 8? Just like we did for the equal to 0 part. Seems like it's equal to 8 right there. So that gives us a starting point. Really, I suppose I should put an open circle there. I'm putting an open circle because we don't have an equal to part in this inequality. So I'm putting an open circle. And since the function is greater than 8, we want to know when the function is above that point. So I'm going to shade that in red. So that is when the function is greater than 8 in that whole shaded region. So what we have now is an interval. We have an interval. And I'm pretty sure this problem has you put the answer in interval notation. So if we have an interval and we want to put that in interval notation, we have to generally figure out the leftmost point and the rightmost point and the x values of those. So the leftmost point, what is the x value? That is 8. We go up here to the rightmost, I see an arrow. That means infinity. So if anything, we put a parenthesis for 8 because there's an open circle, and infinity with also a parenthesis because infinity always gets a parenthesis. So that would be it for part B. So that's pretty much the process of these. It's nothing computational. It might be something you end up doing in my math lab. You might get it wrong the first time. They will show you what the correct answer is, and you look and think, oh, I mixed up this number or that number. And then the second or third time, it should be a little bit more apparent what the process is. Let's move on to part C. Solve when the function is less than or equal to 15. Okay, so let's start with where the function is 15. Seems to be right there. I'm going to fill that in, filled in circle, filled in point, because now we have equal to as well. And we want to know when the function is less than this point. So less than. So now in blue, I have that region shaded. And now we want to represent that interval. So like we did before, we need to find the leftmost part and the rightmost part. The leftmost part seems to be an arrow going to the left. That is negative infinity. The rightmost part, 22, because we want the x value. So negative infinity. For the leftmost part, 22 for the rightmost part. 22 gets a bracket because we filled in the circle, because we have equal to now. So for part D, it wants to know Well, two things simultaneously. When the function is trapped in between 0 and 15. So, let's see. I'll do this in the color black. From 0 to 15, in fact, I might have to erase some stuff. So when the function is 0, seems to happen right here. I'm going to put an open circle there because at 0, we just have less than. 15, when is the function 15? Seems to happen right there. I'm going to put another open circle there because, yet again, we have another less than sign, no equal to part. And now it wants to know when the function is in between those 2 points, which seems to be in this general region. So finally, we represent that region by finding the leftmost x value and the rightmost x value. Leftmost x value is -8. And the rightmost is 22. So again, they're a bit tedious, but there's nothing computational to them. It's just identification. Does anyone have any questions about this one before I move on? Google Meet, okay. Okay, so let's move on to the last question in this section, example 11, which is fairly similar to the one we just did. So what we do here, I think the most complicated part of this one is just trying to dissect what is actually going on. So let's look at A and see if we can get a grasp of what is actually occurring here. So A wants us to solve the equation f of x is equal to g of x. Now the f function, so the f function is this diagonal line. The g function seems to be this lower horizontal line. When they equal, what that corresponds to is when the lines intersect. They seem to intersect right there. And I also conveniently included the point for which they intersect at. Now, when you solve the equation, when you solve an equation, you're normally finding x is equal to something. So it's x is equal to, you're going to take the -8 value. That's what they are looking for. When you solve an equation, you're trying to find what x is equal to generally. So x is equal to -8. We continue with solving this inequality. And the way we solve this inequality, so we have to figure out what it's asking. So it's asking for, so when is the f function, which is the diagonal line, in between the lower horizontal, g of x, and the upper horizontal, h of x. So in essence, what it wants is this point included, because there's an equal to part over there. And then an open circle here, because with h of x, there's no equal to part. And it wants to know the area in between those two. It wants to know when f is sandwiched in between those two horizontal lines, g of x and h of x. And naturally, since we have an interval, we can go ahead and characterize it using interval notation, which means to figure out the left side and the right side. The x value of the left side is -8. The x value of the right side is 4. We use -8 with a bracket because that side had an equal to component in the inequality they gave us. And the 4 has a parenthesis because it did not have an equal to component. So that would answer part B. So again, nothing computational, just more so identification based. So does anyone have any questions with that one before I move on to the next section? Okay, well, that concludes everything on lines and linear functions. So that homework is due tomorrow night. I do have office hours as well. So I do have office hours. I mentioned it. I have an announcement in Moodle just dedicated to office hours. There's also that tutoring center on campus in Tinsley Hall right over there, right next door, that has walk-in appointments, and you could schedule appointments as well. That's through the Center for Student Excellence. Need any tutoring services? So, with that being said, let's move on to library of functions and circles. Now, because the hurricane happened, circles has been taken out, so no circles. So everything in these notes on circles, it's not applicable. I'm not going to talk about it. It's not in your homework. It's already been removed from your homework. So we're not talking about circles at all in this semester, this whole semester. We will be looking at library of functions, though. And there's not really much to say about them other than here they are. If you've taken college algebra before, perhaps somewhere else, you might know of these as parent functions. But these are the basic shapes of some more complicated functions that we look at. The more complicated a function gets, sometimes we want to know, all right, well, what's its shape look like? What's its basic shape look like? And for pretty much every function we're going to deal with in this class, they will reduce down to one of these 8. That section in my math lab, it's all, in fact, I'll show you. It's mix and match. What does that shape pertain to? And then you go here and you find that one. It's like at McDonald's when someone orders some burger and you press the button on the computer. So that one you can knock out in 5 minutes. So that one shouldn't be a problem. And there's nothing really to say about it other than We're going to be referencing this, probably the most important ones, the square and the cube functions. Square is a cup shape, and cube is really it's a snake-like shape. So those are and square root one's pretty important as well. Other ones we might not touch up on as much. So square, cube, and square root. But other than that, there's nothing really to say. And then, like I said, circles are all gone. So this whole page in the notes, just not even going to touch it. So really, the next thing worth substance, has any substance, is graphing with transformations. And so what transformations do, it's a natural extension of the library of functions, because the library of functions give us the basic shape of some function. And then the transformations say, well, what about if I want to take, say, that cup shape and move it to the left or to the right, or up and down, or maybe I want to stretch it out or compress it or reflect it in some manner. Well, that's what this section deals with, taking those basic functions and transforming them in some way. And we'll start off that discussion by talking about shifting. So in particular, vertical and horizontal shifting. So that's, if you take some general function, you go to the left or to the right, or up or down. So the vertical shift, so there's two types of shifting. Vertical shifting, which is up or down. So as you've heard me say before, this is all based off of the idea of taking understandable visual ideas and converting them to an algebraic context. So we all understand that we all have this spatial awareness to interpret up or down, up, down. So how does that translate algebraically? And if you want to take a function and shift it up or down, you simply add that number to the end of the function, or just to the function. So if you want to shift a function up 2, you add 2 to the function. So if a number is added to the function, that will give you up or down. If you subtract a function by 3, then guess what? You're shifting it down by 3. So that's it. Now say that the shift is verbatim, which might make more sense what that means in comparison to opposites for the next one. A horizontal shift, all right, we already talked about left or right, or up and down. Now we're talking about left to right. So again, we all understand that visually, but algebraically, this is when you add or subtract a number to the x variable. So when a number is added directly to the x variable, not to the function, but directly to the x variable. The x has to be right next to the number for that to be a shift left or right. And we'll do a few problems talking about that, no doubt. The shift is opposite. Oops. The shift is opposite. Sorry, I think I accidentally cut off my mic there for a second. Okay. So let me try that one more time. The shift is opposite because, well, before we said if you add 3 to the function, you would go up 3. That's a verbatim operation. Add 3, go up 3. This is not the same for left and right. If you add 3 to the x directly, then you will end up going the opposite direction. Adding 3 means you would go to the left 3, or subtracting 5 means you would go to the right 5. So mainly it's best to see that in context. So let's go ahead and move on to example 1 here. So we're going to figure out for question 1 here and, well, example 2 as well. Let's go ahead and figure out how these translate to the graph. Now, the square root of x, to figure out what its shape is, we would refer to the library of functions. And you could see the square root function is number 5 here. It's this arc shape. So if anything, that gives us an idea of what the shape of this will look like. And then it says take that shape and shift it to the left 8 units. So we're going to take that shape, go to the left 1, 2, 3, 4, 5, 6, 7, 8. And then that shape looked like this. Now in MyMathLab, they simplify this process for you big time. You will notice various shapes. So it has this tool that it has the shapes and it will move things accordingly. You tell it to shift to the left 8 or horizontally to the left 8 units. You should be able to recreate this without much hassle. MyMathLab does a lot of the graph building for you. So if anything, that's the shape. It'll look much better on MyMathLab side. I can't draw it too great on here. So we have that. So that's the geometric side of things. But what about the algebraic? How do we take the square root of x and represent that as a shift left of 8 units? So that's when we think about, all right, left and right. What does that refer to? Do we add the function directly or do we add the x variable directly? Left and right, we have to add to the x variable directly, which means whatever number we add or subtract will have to be in the square root. That's how we add to the x directly. We have to impose it into that function somehow. And if we want to go to the left 8 units, left and right means we need the opposite operation. So left 8 units means we would add 8. Has to be the opposite. So that's what the function would look like. Left or right means we add to the x directly, and we have to do the opposite. We have to apply the opposite operation to the direction. Left 8 means we add 8. That is opposite. And then the problem goes on to say, determine the domain and range based off of the graph. So to find the domain, let's recall from a few weeks ago, the domain is found by viewing the graph left to right and looking at the x values. The furthest to the left we go, I'm shading that in red. That seems to be an x value of -8. And the furthest to the right you can go seems to be that arrow, which would indicate infinity. We will use a bracket with -8 because -8 is part of the graph. All right, so that's the domain. The range, that's bottom to top and uses y values. So the lowest point, I'm again going to shade in the same region because it just so happens it's the leftmost point and the lowest point. And we want to know the y value now. That would be 0. And then the highest point seems to, again, be the arrow. And my graph doesn't do it justice. It does go up, albeit it does start to, it looks like it levels out, but it does go up forever. That would be infinity as well. So we include 0, because 0 is part of the graph, and then it does go up forever. There is no horizontal asymptote or horizontal barrier of any kind. So that would answer part 1, or problem 1 here. So for problem 2, we're going to do the same thing. It's just now they have us do a little bit extra. So now we have x to the 3rd power, or x cubed. We're going to shift down 5 units and to the right 3 units. So naturally, we need to know what the shape looks like. Now, of course, on your end, it may give you more information, but x to the 3rd, so the x to the 3rd function we had, let's go figure out a shape using the library of functions. And it seems to be number 4. Number 4, the cube function. It's the snake-looking shape. So if anything, now we know what the general shape looks like. And so now the question is, what do we do with the shape? Shift it down 5 units and to the right 3 units. So let's take that, shift it down 5 units, 1, 2, 3, 4, 5, and to the right 3 units, 1, 2, 3. And now that is where the graph will occur at. Again, my graph isn't very good. It will illustrate this much better in my math lab. So now let's think about the more important parts. How is this affected algebraically? So it's asking us to go in 2 directions, down and right. Well, if anything, let's do down 5 first. We can build this thing one at a time. So what does it mean to go up or down? This one's generally the easier one. Going down means you would just subtract 5 from the function itself. So this would be down 5, where we just take the function and we subtract 5. This is a verbatim operation. Up and down implies if we want to go down 5, we just subtract 5. We don't have to do any opposite stuff. So this would be down 5. Down 5. From here, well, we still have to go to the right 3. So this is when we have to add to the x variable directly. So the way that looks like is, well, that number that we add to the x will have to be under the 3rd power as well. I have the parentheses here to represent that. Now to go to the right 3, left and right means we have to do the opposite operation. So to the right 3 means we would have to subtract 3. And that would be to the right 3. Right 3. And so what we have on the far right here, so that would be the function that corresponds with this newly transformed shape. And from here, we can go ahead and figure out the domain in the range. Now, if we look, so domain is left to right. Well, it just so happens when I look to the left, I see an arrow. When I look to the right, I see an arrow. Furthest left is here, furthest right is here. There's no barriers. Again, my graph doesn't really illustrate it too well, but we get two arrows. Negative infinity to positive infinity. With the range, it's actually going to be the same idea. How far down can we go? We get an arrow. How far up can we go? We get an arrow. So it is also negative infinity to positive infinity. This is actually true for any cubic function. It always has an unlimited domain and range. Does anyone have any questions about either of these two? Okay. Well, let's go ahead and move on to the next example. Okay. 1, 2, 3. Okay, cool. So let's move on to the next example. So we talked about the cardinal directions already, and we're going to keep practicing left, right, up, and down. We're also going to throw in how to apply or interpret the compression or stretching of a graph. So really, this sort of idea, compression and stretching, is whenever you multiply the function by a number. So when you multiply, so with all the shifting that we talked about before, that was all addition. So stretch and compression, that's multiplication. And there's two types of vertical, well, there's two types here. There's vertical compression. So you can see vertical compression is when you multiply by a really, really small number, as you can see. A number between 0 and 1. That would be a compression. Like 1/2, for example. If you multiply it by 1/2. Vertical stretch would be, well, if you multiply by anything bigger than 1. That's a stretch. So let's go ahead and look at example 2 here, where we're going to graph this function and determine a bunch of stuff about it. So they give us this function, as you all hopefully can see. And they even tell us what the basic function is. Y is equal to x squared. So if anything, that tells us the shape. We're going to come back to that, though. For right now, we're going to look at part A, and it's asking us to determine the transformations given the graph. So not build the graph from the transformations, but determine the transformations from the function. So as we read on, it should be horizontally shifted to the left or right. When we look at this function, we need to look at which one of these numbers actually corresponds with left or right. And it seems to be, remember, left or right, it's the number right next to the x, or being added or subtracted directly to the x. So x minus 3 would give us that idea. So if anything, it's x minus 3. So that tells us the idea of left or right. Since it's minus 3, it means this is going to be to the right 3. So to the right by 3 units, as it goes on to say. Additionally, it goes on to ask for a vertical stretch or compression. That comes from what multiplies the function, which is that 3 in the front. It's 3 times. It's a stretch if that number is greater than 1. So 3 is, of course, greater than 1. So it's stretched by a factor of 3. Finally, it goes on to ask about how much up or down we go, and that's what's added to the function as a whole. So that's the +1 here. This is a verbatim operation, which means +1 implies up by 1 unit. So that would answer part A. It's just breaking down how to interpret the function. So part B, you may notice there's this box over here to the right. You may notice this box. And what this box does is, after you pick the shape of the function, so it'll have a few shapes on the interactive table. You pick the shape, you fill in these various fields in the table, and it will construct the graph for you. So, if anything, what the shape is going to be, well, earlier, it told us that the basic function is y is equal to x squared. If you look at the library of functions, x squared looks like a cup in a sense. It's the one that looks like a cup. It's called a square function. So, if anything, we know that the shape, is going to look like that. And there will be that illustration on the tool, and you click on it. And once you click on that shape, then this box will appear. And then we could start filling in everything one by one. So the first one I see, we'll do this one by one, vertical stretch or compression. Vertical stretch or compression. It doesn't even care which one's which. It just says whatever the factor that you found was, and we found that to be 3. In fact, I'll do this in the color scheme that I did when I circled all the answers. So just make it clear which one's which. So let's see. For the vertical shift, for stretch, I did red. So I circled stretched in red. So vertical stretch compression, we found 3 for that one. It's stretched by a factor of 3, as we circled in red. So that 3 would go really right there. Now the vertical shift, you may notice it's a slider. You simply just slide it to the number, and as you change any of these numbers or interact with this box in any way, the graph will concurrently move along with it. So when you move the horizontal shift slider, it will start moving left and right. And the rest of it, so it will interact in real time. So the next one I see is the vertical shift, which I used purple. So the vertical shift, so that refers to how much up or down we go. We determine it goes up once, so 1. And there's the horizontal shift, which we said this goes to the right 3 units. For the horizontal stretch, the horizontal stretch or compression, we just always leave that 1. It just doesn't come up in this class. Just always leave that as 1. And we'll talk about the reflect stuff. That comes up later in this section. So we'll leave that alone for now. But other than that, once you fill out those corresponding fields, you will get, let's see, we go to the right 3. And what was that? Up 1. And since we know it's the cup shape, you will get something that looks very close to this. Does anyone have any questions about this so far? There's still 2 more parts to this problem. If not, let's go ahead and address those parts. So let's see, the graph that we had, which will be relevant later. 3x minus 3 plus 1. So I'll just redraw this, because that'll come up in a bit. So for part C, find the missing coordinates. So part C is asking for how, since we're dealing with transformations, it's how do points transform once you shift. And so, as you may notice, the parent function that we dealt with was y is equal to x squared. So they want you to plug in those x values in. So if you plug in, say, -2 into x squared, you're going to get positive 4. If you plug in 0, you'll get 0. And if you plug in 2, you get positive 4. That's how this problem starts off. The corresponding points, that one's going to be a little bit different. Because, well, we shifted to the right 3. And because we shifted to the right 3 in this problem, the x values that are over here will also shift to the right 3. What happens if you shift -2 to the right 3? Just get 1. So that's your new x value. And if you shift 0 to the right 3, you get 3. If you shift 2 to the right 3, you would get 5. And from there, you're just plugging all of those into the function we started off with. This is seeing how these points transform after, well, we apply all the transformations. So we're not plugging those into the y is equal to x squared. We're plugging those into the original function we were dealing with, this 3x minus 3 squared plus 1. So now we plug 1 into that and see what happens there. 1 minus 3 is -2 squared is 4, times 3 is 12, plus 1 is 13. So you just plug in 1 into that function, you should get 13. This one's easy, it's 1 because 3 minus 3 is 0. You add 1. 5 minus 3 is 2 squared 4. 4 times 3 is 12, plus 1 is 13. So that's just calculator work. but the complexity of part C is determining what the new x values will be. And the new x values are determined from the old x values by how much you shifted left or right. How we got from -2 to +1 is because we shifted to the right 3 units. So we'll go ahead and knock the domain and range out. Since we have the graph, we can go ahead and figure out the domain and range fairly quickly. So the domain is furthest to the left versus furthest to the right. The furthest to the left, I see this arrow. There's no barriers or anything, so that's -infinity. Furthest to the right, I see another arrow. +infinity. So that one's not too bad. The range, how far down versus how far up. So it's not going to be -infinity. The furthest down is right here. So what's the y value of that point? Seems to be +1. What's the y value of that point? So it's a +1. Which will have a bracket because 1 is included in the cup shape, the parabola as it's called. And what's the highest up we go? Well, we have arrows going straight up. So that's infinity. Does anyone have any questions about this one? Because if not, what I'm going to do on Friday. So Friday, I need to finish this section. So I'm going to lecture Friday. And after that lecture on Friday, I'll stick around and answer any homework questions you may have. So if you have homework questions, bring them. Because this homework, once we finish this will be due on the 5th. The 5th being Saturday. So if none of you have any questions, you're welcome to leave. I'll send out the link for the Friday session to where everyone's included. So look for that. Other than that, have a good day.
Get the workbook from the what's it called? The bookstore.
Bookstore. Yeah, try to get that. Since I posted the workbook assignment in my math lab just for this first time, that means you won't need it until next week. Try to get it soon, but that's when you will need it.
All right. Thank you.
Yep. The notes are in they're in my math lab. Yeah, course note. Yeah, as soon as you click on that, you'll see it. You can download it, do whatever. And Brianna, you were talking about corresponding points. How do you find the y values? So you plug those into where's that? You plug those into this function here. So x is equal to 1. When you plug x is equal to 1 into here, 1 minus 3 is -2. -2 squared is 4. 4 times 3 is 12. Plus 1 is 13. So that's how you find the corresponding y values for those, if that's what you were asking. Yep.